Can you identify with this? Your AI agent works perfectly in the demo. It reasons, it plans, it executes. The stakeholders are impressed. Then you deploy it to production, and within hours, it's looping endlessly, skipping steps, contradicting itself, all symptoms of lost or corrupted state, and nobody can figure out why. The prompts haven't changed. The model hasn't changed. So what bloke? The answer is almost always state management. Not the model's intelligence, not the prompt's cleverness, but how your system tracks where it is, what it's done, what it believes, and what it should do next. In practice, state includes the working memory, the goal, constraints, intermediate results, tool outputs, decisions made so far, and any facts the system is relying on. State management is the hidden foundation that makes everything else work, or makes everything else fall apart. Here's the fundamental challenge. Traditional software is deterministic. Given the same input, you get the same output. But agentic AI systems are probabilistic. The LLM might reason differently each time. It might choose different tools. It might produce outputs that vary in structure or content. When your control flow depends on probabilistic outputs, traditional state assumptions collapse. You need architecture that traditional software never had to solve. This video is about Skill 1 in the framework of 9 essential skills for agentic AI strategists, multi-agent orchestration and state management principles. This isn't just the first skill because it comes first alphabetically. It's first because everything else, memory, tools, security, observability, builds on top of it. Get this wrong, and no amount of sophisticated tooling will save you. Let's understand why the patterns you learned for traditional software don't work for agentic systems. In classical programming, state is deterministic. A function processes data, updates variables, and the next state is fully predictable. Debugging is hard, but fundamentally traceable. Now consider an agentic system. An LLM decides what to do next. It might call a tool, or it might not. It might ask for clarification or proceed with assumptions. It might produce output that matches your expected schema, or it might hallucinate something entirely different. The next state isn't determined by code. It's influenced by a model that is fundamentally stochastic. This is why the demo to production gap is so painful. In a demo, you run 5 or 10 examples. The model performs well, edge cases don't appear, and everything looks smooth. In production, you run thousands of interactions. Every edge case shows up. The model's variability compounds across steps, often exponentially. Without proper state architecture, those small variations cascade into system failures. The solution isn't to make the model more predictable. That's fighting against the fundamental nature of LLMs. The solution is to design state architectures that expect and handle non-determinism. You need explicit state schemas, validation at every transition, checkpointing for recovery, and observability to see what's actually happening. This is engineering discipline applied to probabilistic systems. Modern agentic AI frameworks have converged on 3 primary paradigms for managing state. Each has distinct advantages, and the most sophisticated systems often combine elements of all 3. Each paradigm optimizes for different trade-offs: determinism, scalability, or developer ergonomics. Let's examine each paradigm in depth, starting with the approach that has become perhaps the most influential: stateful graph architectures. Stateful graph architectures, pioneered by frameworks like LangGraph, represent agent workflows as explicit state machines. Each node is a computational step, calling the model, using a tool, making a decision. Edges represent transitions between states, including conditional edges that route based on the current state's content. The agent reasons, but the graph decides what happens next. The graph is the source of truth for what the agent should do. The power of stateful graphs comes from their determinism and auditability. You can visualize the entire workflow. You can trace exactly which path execution took, and crucially, you can checkpoint the state at any node and resume later. If the system crashes, you don't lose everything. You roll back to the last checkpoint and continue. This fault tolerance is essential for production systems. The second paradigm is event-driven state management, exemplified by systems built on Kafka, Redis streams, or frameworks like Llama Index Agent Workflow. Instead of a graph you traverse, you have a stream of events. Each action the agent takes, receiving input, calling a tool, giving a response, making decisions, producing output, is recorded as an immutable event. The current state is derived by replaying these events. Event-driven architectures excel at four things. First, temporal replay. You can reconstruct the state at any point in time by replaying events up to that moment. Second, distributed processing. Events can be consumed by multiple services simultaneously. Third, natural audit trails. The event log is a complete, immutable record of everything that happened. And last, they are flexible and agile, where you can easily add or modify services without disrupting existing workflows. For compliance-heavy industries, this is often non-negotiable. The trade-off is complexity. Event systems demand discipline in schema design and replay logic. The third paradigm is context-based state, championed by frameworks like Agentic AI. Here, state is modeled as explicit data objects, typically Pydantic models with strict type validation, that are passed between components through dependency injection. The state isn't hidden in a graph or a stream. It's a first-class object that components receive, modify, and return. Context-based state brings software engineering best practices directly into agentic systems. Type safety means you catch schema errors at development time, not in production. Dependency injection means components are modular and testable in isolation. Explicit context passing means there's no hidden state that can cause mysterious bugs. If you come from a typed language background, this paradigm will feel immediately familiar. This approach works best when workflows are explicit and becomes harder when control flow is highly dynamic. State management isn't just about storing data. It's about controlling how agents move through workflows. Control flow patterns define how agents collaborate, when they execute, and how results are combined. Let's examine the four primary patterns, starting with the simplest: sequential pipelines. Sequential pipelines are the simplest pattern. Agent A completes its work, passes output to Agent B, which completes its work and passes to Agent C. This linear flow is perfect for well-defined step-by-step processes, document summarization, data transformation, or any workflow where each step depends entirely on the previous one. When tasks can be decomposed into independent subtasks, parallel execution with fan-out and fan-in dramatically reduces latency. A manager agent decomposes the work, spawns multiple worker agents simultaneously, waits for all results, then aggregates them. Processing 10 documents in parallel takes the time of 1, not 10. Hierarchical delegation mirrors how human organizations work. An executive agent receives a complex goal and decomposes it into sub-goals. Manager agents take those sub-goals and further decompose them into tasks. Worker agents execute the tasks. Results flow back up the hierarchy. This pattern scales to enterprise-level complexity, handling goals that no single agent could accomplish alone. The most sophisticated systems use dynamic and adaptive topologies. They don't pick one pattern and stick with it. Instead, a meta orchestrator analyzes each task and selects the appropriate collaboration pattern. A brainstorming phase might use a network mesh where agents freely exchange ideas. An execution phase might switch to hierarchical delegation for control. A review phase might use a sequential pipeline for systematic checking. Dynamic topologies require strong state contracts. Without them, flexibility turns into chaos. State management enables collaboration, but communication is how agents actually exchange information. The communication pattern you choose affects latency, scalability, and fault tolerance, and whether shared state stays coherent. Let's examine synchronous versus asynchronous patterns first. Synchronous request response is simple. Agent A calls Agent B and waits for the answer. This works well for quick, low-latency interactions where blocking is acceptable. But for long-running tasks, synchronous patterns create bottlenecks. If Agent B takes 30 seconds to respond, Agent A sits idle the entire time. Asynchronous message passing decouples the sender from the receiver. Agent A puts a message in a queue and immediately continues with other work. Agent B processes the message when ready and puts its response in another queue. This pattern scales horizontally. You can add more workers to process messages faster, and handles failures gracefully since messages persist in the queue. The Blackboard architecture offers a fundamentally different model. Instead of agents sending messages to each other, they read and write to a shared memory space, the Blackboard. Each agent watches for relevant updates and contributes partial solutions. This collaborative approach excels at problems where multiple perspectives need to combine, like complex planning or creative brainstorming. Without strong access controls, Blackboards can become noisy or unsafe. Finally, handoff mechanisms address a critical challenge. How does one agent transfer control and context to another without losing information? A well-designed handoff includes the current state, the goal being pursued, relevant history, and explicit instructions for the receiving agent. Poor handoffs are one of the most common sources of agent failures. The receiving agent lacks context and makes decisions that contradict earlier work. Let's translate these principles into practical guidance. First, the common pitfalls. Overcoupling to frameworks is dangerous. When you mix business logic with framework-specific APIs, you can't switch frameworks without rewriting everything. Always abstract framework-specific code behind clean interfaces that express your domain logic. Over time, framework coupling becomes a tax on every change you make. Ignoring non-determinism is the pitfall that catches even experienced developers. You test with 5 examples, everything works, you deploy. But you never tested the edge cases where the model returns unexpected formats, makes different choices, or produces outputs that don't match your schema. Every state transition should validate that the output conforms to expectations before proceeding. Poor state schema design creates problems that are invisible until production. If your state representation is unclear or inconsistent, different parts of the system interpret it differently. This is a fatal occurrence in a production system and is sure to send the developer back to the drawing board. Good schema design paves the path to consistency in production environments. You must define your state schemas explicitly, preferably with type-checked models like Pydantic. Document what each field means and when it should be populated. Everything is laid out and well-defined. There is little chance of misinterpretation in a good schema like this. Your future self debugging at 2 a.m. will thank you. For your implementation checklist, before committing to a framework, design your state schemas. Model your workflows as finite state machines or event flows. Define clear agent roles and communication protocols. Specify what happens when things fail, because they will fail. Add observability from the start, not as an afterthought. And build abstraction layers that let you change frameworks without rewriting your core logic. State management is the foundation that determines whether your agent system will be a reliable production tool or a fragile demo that breaks under real conditions. The patterns we've covered, stateful graphs, event-driven architectures, context-based state, control flow patterns, and communication protocols, are not optional extras. They are the engineering discipline that separates AI systems that work from AI systems that can be trusted. Master these principles, and everything else in the agentic AI landscape becomes easier to build, debug, and scale. Reliable systems compound value. Fragile systems silently destroy it. We've covered a lot in this video, but here's the takeaway. Agentic AI systems don't fail because the model isn't smart enough. They fail because the system around the model isn't designed to handle reality. State management is what turns clever demos into reliable production-grade systems. It's what allows agents to behave consistently, recover from failure, collaborate safely, and scale without chaos. Get this right, and every other skill in the agentic AI stack becomes easier to build and reason about. If this kind of deep, practical thinking about AI systems is valuable to you, make sure you subscribe to the channel. Give the video a like if it helped clarify how real agentic systems actually work. And don't forget to ring the notification bell so you'll know when the next video drops. In the next episode, we'll continue building on these foundations and move deeper into what it really takes to design AI systems you can trust in the real world. Thanks for watching, and I'll see you in the next video.